The decimal system that we all know and cherish is a positional system based on 10. This is probably because we have 10 fingers, and historically, as now, people often count on their fingers. Mathematically speaking, there is nothing special or magical about the number 10. The process of adding, subtracting, multiplying, and dividing is the same regardless of base, such as base 5. So here is the number 423 using different bases converted to base 10. 423 base 5, positional, is essentially the number on the far right is ones place. The number over is whatever is going to be multiplied by whatever the base. And the next one over would have multiplied by the base squared. So if I say 423 base 5, that really means 4 times 5 squared plus 2 times 5 plus 3. And that comes out to be 113. 423 base 6 is 4 times 6 squared plus 2 times 6 plus 3. Put it in the calculator, you get 159. 423 base 7 is 4 times 7 squared plus 2 times 7 plus 3, 213, and so on. Notice that 423 base 10 is 4 times 10 squared plus 2 times 10 plus 3. Comes out to be 423. Not accidental. But I can continue on. 423 base 11 was 4 times 11 squared plus 2 times 11 plus 3. That comes out to 509. And you can continue on with whatever number you want to use. For this lesson, we're going to stick with the base 5. But this can apply to any base. Let's think about base 10 in terms of coins. So one way to see the difference between base 10 and base 5 is to think about coins. Base 10 would be like a pocket full of dollars, dimes, and pennies. So something that costs 368 cents would be paid with $3, 6 dimes, and 8 pennies. So where a dime is 10 pennies, a dollar is 10 dimes, those are powers of 10. Consider a world where change is made up of pennies, nickels, and quarters. So let's say a nickel is 5 pennies, a quarter is 5 nickels. So for our purposes, we'll say dimes don't exist. Each time we have 5 pennies, we can replace it with 1 nickel. And each time we have 5 nickels, we can replace it with 1 quarter. In base 5 notation, the leftmost digit of a 3-digit number can be used to represent a number of quarters. The next digit represents the number of nickels, and the last digit represents the number of pennies. So if you have 213 base 5 is 2 quarters, 1 nickel, 3 pennies. And as changed, 2 quarters is 50 cents, plus 5 more cents for the nickel, plus 3 more cents, that's 58 cents. You see, 213 base 5 is the same thing as 58 base 10. So if we were to make change for 113 pennies, we would need 4 quarters, 2 nickels, and 3 pennies. That is, 113 is 4 times 25 plus 2 times 5 plus 3. So just as 4 times 100 plus 2 times 10 plus 3 can be written as 423, 4 times 25 plus 4 times 5 plus 3 can be written as 423 base 5. And we read that as 423 base 5. So unless expressly stated to the contrary, a number written without a subscript will be read as base 10. So how many quarters, nickels, and pennies are needed to get 64 cents? And we want to get the minimum number of coins for each of these. But it's a quarters, nickels, and pennies. For 64 cents, I would need 2 quarters, and that leaves us with 14 cents. So 2 nickels and 4 pennies. So 224 base 5 is equal to 64. 114 cents, you would need 4 quarters to get you the 100, and then 2 nickels for the 10, and then 4 pennies. So 424 base 5 is equal to 114 base 10. For 91 cents, I would need 75, so 3 quarters, and that would leave me with 91 minus 75 is 16. So that would be 3 nickels and a penny. So 331 base 5 is the same thing as 91 in base 10.